Okay, so today we're going to be talking about predicting products. So some things you need to know. You need to know the 5 types of chemical reactions. If you remember, these are the 5 types. We have combustion, we have double replacement, single replacement, decomposition, synthesis. We have all these different types. Now, if we take this away, what you're going to see is these patterns, they all look slightly different from each other in our reactant side of the line. So we can use this pattern that we see to help us predict what products we're going to have at the end of these reactions. So I also need to remember how to write ionic formulas. I need to find common charges on my periodic table. I also need to be able to balance those equations and find polyatomic ions. And to do this and to have in front of me, I'm going to have my annotated periodic table. It has the charges up top. It has what is metal, non-metal, etc. Also has those polyatomic ions on the back. You might have a list that's separate. That's okay. And then you also need this activity series chart for when we start working in those single replacement reactions. So let's take a look, because we're going to need a process. I always like to have steps for something because it helps me organize my thoughts and where I need to go. So the first thing I need to do is identify the type of reaction. Then I just need to figure out, can this reaction even happen? Now for our class, we're going to be concerned with single replacement reactions. Can this reaction happen? Just know that that's not the only equation that needs some qualifiers. It's just the only one that we're going to be evaluating. Then we're going to write out the products. And if there's ionic formulas, you need to balance out those ionic formulas. You should also remember if something is diatomic. So fluorine, for example, fluorine should be F2 if it's by itself. And then lastly, we need to balance the chemical equation if we're asked to. So let's take a peek at a single replacement reaction. So I'm going to write one out here. We have copper plus magnesium nitrate, so NO3, 2. And first thing that I need to do is I need to identify that this is a single replacement reaction. So I'm looking at it, I see one element here, and I see it being with an ionic compound. So I'm going to take a guess that I think this is a single replacement reaction. So now I'm going to consult the activity series. So we have copper. Copper is way down here. And then we have magnesium. Magnesium's all the way up here. Oh, man. So here's the problem. Copper is not above magnesium. Magnesium is too strong to be kicked out of this seat. So therefore, this is no reaction. That's just the abbreviation for reaction, RXN. We're done here. That one is all set. So let's look at a different one. So Ca plus, and we'll do HNO3 this time. Okay, so is calcium higher than hydrogen? I consult my list. So hydrogen's way down here. Calcium is way up there. Absolutely, calcium can definitely kick hydrogen out of the way. So I like to just make a little line showing that these two are going to get replaced. And then I have to figure out how to write these new pieces. So I'm going to have Ca, and I'm going to have NO3. So I need to find out what the charge is on these if I'm going to make the product. Now my other thing though, so Ca and NO3 are going to combine together. H is going to get kicked to the side. Well, that's a diatomic, so that has to be H2. Now let's put these other ones together. So I'm going to use my periodic table. Calcium is in this +2 column, so that has a +2 charge. NO3, that's a polyatomic ion, so we're going to go NO3 up as a -1 charge. So now I'm going to bring those charges down and balance them out. We've done this before in a previous video, so I'm going to be going a little bit more brief with this. So I need 2 of these NO3s, right? So the actual equation should be Ca NO3 too. So if you need to refresh that, please review the video for balancing ionic formulas. So we're going to add this to our end. So we got Ca plus NO3. We have 2 of these. All right, now we can kind of look at what's going on here. We can kind of balance this out. So I'm going to draw my models underneath here. So I have calcium. Over here I have a hydrogen and an NO3. We have our reaction. I have a hydrogen. I have a hydrogen here. And last but not least, I have a calcium. And I have 2 of these NO3s on here. Now, I do like to keep the polyatomic ions like this, so it's not a true model of what I would expect, but I like to keep them clumped together just so I know that they're traveling as a pair. You can see NO3 here, you can see NO3 here. So when I balance them, it's easier to keep them together. Let's see. I have 2 NO3s here, so I'm definitely going to need another one of these. All right, so I have 2 NO3s, 2 NO3s. Let's see our calcium, calcium, hydrogen, hydrogen, and we're actually balanced. So we really need an extra little piece to this puzzle, which is over here. So we just needed to add that 2 out in front. Now we have a nice balanced equation. So that's our single replacements. Let's take a peek over at our double replacements. Now double replacements are slightly different because we have 2 ionic compounds being combined together. And remember, they have to be aqueous. So these have to be in their liquid state. So I can just put a Q over here. We can just put an AQ over here. Okay, just so that we remember that they're supposed to be aqueous. Now, I find it easier if you underline the anion here. It's the last part. And over here, it's the first part that's going to mix. So the inner, they're going to mix together. And then we also have the outers. They're also going to be mixed together. So we're going to balance these out. So we're going to start there. Okay? So I have K. I consult my periodic table. I know that K has a +1 charge. It's going to be mixing with NO3. Now you do always want to write the cation first. So I always think positive before you're negative. So be positive before you get negative. Kind of like a compliment sandwich, right? So we have these. We're going to try to balance them out. Look at that. They are already a nicely balanced charge. So we have this potassium here being mixed with this nitrate. They have equal charges, so I can just write that one out. It should be K, sorry about that, NO3. And then the other part, so the other equation that we got silver, Ag. It doesn't say it on yours, but Ag, so silver, does have a +1 charge. And we can also figure that out because if this is an ionic equation and this polyatomic ion has a -1 charge, the only way that it can be balanced is if this one right here also has a +1 charge. So we have that. And then we also have PO4, and this has a -3 charge after you look at your polyatomic ion list. And we're going to have to put these together. So I have a -3 charge here. I have a +1 charge here. So we got to balance these a little bit, see what we can do. I need 3 of those to equal that out. So my formula should be Ag3PO4. So we get Ag3PO4. Now we have to balance them out. So let's take a quick peek what we got here. PO4 is balanced. NO3 is balanced. NO3 is balanced. Ag is not balanced, so let's take care of that. Let's see, we got, sorry, is Ag a 3? Ag3 is not balanced, so let's take a peek at that. So we got here. So we got Ag3, so Ag3 is now balanced. Ag is good. PO4 remains the same. Potassium needs 3 as well. All right, so we have 3 Ags, 3 Ags. We have NO3. We have 3 NO3s. We have PO4. We have 1 PO4. We now have 3 potassiums and 3 potassiums. Now we're balanced. So our double replacement is done. We are good with that one. If you were doing this later, you may want to check solubility rules if you're doing this for a different class. Now we have a synthesis. So let's take a look at a synthesis reaction. So we have Li plus O2. And these are nice because you're going to see the two different things, so two different elements coming together. And what's nice about it is you're just balancing and making the thing. So you're making lithium oxide. So we have lithium, which lithium has a +1 charge on it. Oxygen over here is a -2. We have to balance these out, right? This has my +1. This has my -2. This is going to be one of those for every 2 of these. So we should have Li2O. We got to balance these out. We got 2 lithium, 2 lithium. Oh, we made a mistake, right? So we have 2 oxygens now. We have 4 of these. So I'm going to just cross that out, put my 4. So we have, that's our equation. And now we're balanced. So that's a synthesis reaction. So remember, those two things are coming together. I'm just writing the formula for if they were to come together. So let's take apart something. Let's look at a decomposition. We have AlBr3. So we're just breaking this apart. So I'm identifying it by seeing that there's one compound over here. So I'm just going to break it apart. I have Al, aluminum, and the other one has to be Br, and because it's diatomic, because remember, we're breaking this apart into its elements, right? We're taking it all the way apart. So this has to be Al over here plus Br2. We're not turning this into different pieces of ions floating around. We're not disassociating them. We're decomposing them, so they're going to become their elements again. So now we have to balance these out. So I have 2 and a 3. So if you remember doing those 2 and 3s, we always switch them, right? So we have 3 over here for Br now. We have 6 total for Br. We have 6 total for Br over here. That gave us 2 aluminums, so I need a 2 aluminum over here. So decomposition, remember, you're pulling them apart into their elements. They're turning into elements. They are not ions anymore. So they have gone through a process where they've gotten the necessary electrons to be pulled apart, and now they're just no longer together. They've decomposed. And then last but not least, probably your favorite one, because the products are not going to change. We have some type of hydrocarbon for combustion. It's going to be added to oxygen. And then to predict the products for this, nice and easy, just write CO2 on one side plus H2O. Always. Doesn't change. Combustion is our favorite friend because it's easy to look at, because I can see the hydrocarbon here, I can see oxygen over here. I know that everything is going to work out okay. All right, so now all I have to do is just balance this. Let's see, I have 2 C's here. I need 2 on this side. So now I have 4 oxygens here, but I also still have water involved because I have this. Let's do a 2. So now I've balanced out this to these. So no matter what, this ratio for these are always going to be the same. Now I just need to make sure about my oxygen. Does this work? Let's see, we got 4, right? So we have 2 times 2 is 4 oxygens here. And then I have 2 more, so that's 6. So I need this to be 6. We have 3, so these are our coefficients for a nice balanced combustion reaction. So that's really what it is. I went through these kind of quick. It's on video, so you can always go back and look. They're really just examples of me working through these. We did talk about them in class. But really, it's all about identifying the first part. What's going on here? What type of reaction do we have? If you have a single replacement reaction, does that reaction happen? And if it does, then we go back and we consult our periodic table. We write out those products, and then we balance the full chemical formula, the full chemical equation. So that's how we do it. That's how we predict products. Now this video is a little longer. I did it for all of them. Please go back and review as needed. Ask questions in class. Let's do this together. I think you guys are doing a great job. Keep it up.